Okay, perfect. Yeah, I think everyone can hear me, and hopefully you can see my screen now. And if we are, then I think we are good to start. All right, so a bit about me. And before I go on, if you can't hear, just make sure to let the team know on the chat, and they should help you get sorted. Now, a bit about me. My name is Chidi. I work as a software engineer, and I used to work at a fintech in Lagos called AOL, and I was there for just about 2 years. I worked as a backend developer. I built backend software for the fintech in TypeScript and Go in a variety of different products we had at the time. And a couple years ago, about 2.5 years ago now, I moved to London to work for a year. And I currently work there. Just a sec, sorry. Yeah, sorry about that. Yes, I currently work there for an investment bank. Also, if there's anything wrong with the audio, please let me know via the chat. I think someone mentioned they can't hear currently. But in any case, I'll just go on. And, if there are any issues, just let me know. Cool. So I also write a programming blog on my website, chidiwilliams.com. I haven't been as active as I used to be this year, but I do frequently would write a post and share on my blog. Besides that, I also co-organize SysDesign. So the group of 3 that sort of runs the Twitter spaces, run a Twitter space. We also run broadly, I guess, the community around Twitter space. We've done that for a couple years now, called SysDesign. We typically have monthly sessions on Twitter spaces where we usually invite someone or get other people to come speak about different technical topics. And myself and Ayo and Bayo, who, if you saw the introductory session, you would have met. All 3 of us run that program. And SysDesign is also the group that is responsible for this conference. So SysConf is sort of broadly organized by SysDesign. So we are, of course, we feel great to have everyone here. Also, I often build, I guess you could call them hobby projects. So I typically build more projects in web animations I've done in the past. I've also been very interested in compilers and languages generally. And more recently, I've also, with the, of course, the recent AI boom, I've also built a number of projects or tools in AI. And one of them is the reason I would be giving this talk today. So hopefully all of you find that interesting. Another thing about me, I guess more on the fun side, is I love to play music. I play both piano and guitar, and I find it very fun to play. Cool. So in terms of what to expect for today's talk, we will be going over, broadly speaking, some of the basics of machine learning. And my talk here will be very focused on audio tasks specifically. So machine learning applied to audio-based applications. We will talk quite briefly about some of the recent advances and applications of machine learning in audio applications, and specifically would go over a bit about Whisper itself. So Whisper is a model that I'll talk about a bit later, but it is essentially it's a speech-to-text audio transcription model. I will also talk about some of the open problems and opportunities in machine learning. So this would be more about, I guess, an introductory talk to machine learning, and then hopefully I might inspire someone or some people to get interested in machine learning applications, especially in audio, and find things they find interesting in it, whether that is for more hobby-like projects or other more, I guess, like financially productive means as well. Finally, I'll talk about how to contribute. I'll speak maybe briefly about that, but it will just be some of the places I think are most accessible to contribute and how to get started generally as someone who is interested in such topics. So yeah, let's talk about how I got here. I spoke a bit about my experience, my experience working in back-end development. So I come from a more fintech finance background, and I currently sort of work in this AI-based set of applications. Now, in terms of how I got here, I guess it starts September 2022. So in September last year, OpenAI, the company behind ChatGPT and a variety of other AI tools, released Whisper. And Whisper itself is a multilingual speech-text transcription model, which means essentially that it can transcribe, so you can convert text in some language into convert audio in one language into text in the same language, but you can also do translation. So it can, if you provide it with audio in French, for example, you can ask for it to be converted into English text. After the model was released, I saw a tweet, as we often do, about wanting to have the model packaged as a desktop app in a way that will be more friendly, because Whisper was released as a Python library. So you would go to your terminal, you type in pip install OpenAI Whisper, and then Whisper run audio.wave or audio.mp3, and you get transcriptions. But just to make it more accessible to people who are maybe not as technically savvy to use the terminal and want to rather use the transcriptions in more desktop-based environment, that would be sort of more helpful to them. And I did think it was really interesting, both because someone mentioned it, but also I did feel like, personally, it's also something I would be interested in having as a tool. And so a few days later, I had worked on a simple demo-able version of a Mac app for the to package the model, and it was called Buzz. I posted a tweet about it. I posted a tweet about it on Twitter, and it got somewhere around 20k video views and 100k impressions, and it got a bit like viral in terms of people wanting to try it out or use it. I also posted it, made it open source on GitHub, so people were able to sort of download and use the application. Now, fast forward to today, September 2023, just about a year after that happened. Today, the project has continued to go on. It's gotten right now about 130k downloads on GitHub. What I really want to do today is talk to you about the timeline of the year. So in the duration between September 2022 and now, what are some of the things I've learned and how have I applied them? What have I found interesting in the space? And just as a disclaimer, I would say that I generally am still relatively new to the scene. So like I mentioned, I've only been working on this project, you could call it, for about a year. But there is still a lot more I have to learn in terms of learning about how these ML models work and how they applied for audio processing tasks. But hopefully what I would have what I would go over in this talk would be useful enough to get someone interested in topics like this and maybe picking up some of these applications. Now, we can start with a landscape of audio ML. Something you would find quite quickly learning about machine learning is similar to other technical fields. There is a wide variety of different subtopics under the field of audio ML specifically. Now, I'll outline some of them, and then we would go deeper into only one of those topics. But under audio ML, you can find, for example, a set of tasks that have to do with classification. So classification in terms of figuring out what class does something belong to, what group does something else belong to. And some of those tasks might include something like speech or non-speech. So trying to figure out, like, is some particular audio about or featuring someone talking, or is it audio of something else? So is it audio of trees, branches of trees moving with the wind, or is someone speaking the audio? You could also be classifying speakers in the audio. So you might have a piece of audio and trying to figure out, is the person speaking in this audio person A, or is it person B? You might also want to recognize emotion through audio. You might want to figure out whether the person speaking is sad or happy or feeling some other kind of emotion. We also have tagging. So you might have groups of audio clips, and you want to tag them by some specific features. Under ML, there's also the class of tasks that have to do with detecting or segmenting things. Now, detecting might be in terms of voice activity. So at what point in some audio clip is there a voice speaking, and at what point does the audio become silent? You might also want to detect music. So many people might already be familiar with tools like Shazam or tools like Siri's song search, where you can play some audio into some system and figure out what music is playing in that particular audio clip. You might also want to do speech segmentation, where you're trying to figure out, like, in this speech, what are the different sort of parts of language, or parts of grammar, parts of speech that are present in this audio clip. We also have fields that have to do, or tasks that have to do with recognizing and transcribing audio. One of those things could be sort of automatic speech recognition, which is what we're going to really focus on today, which is about figuring out how to turn audio in some format into text, which is another format. You might also have some form of music recognition, and another subfield within audio ML would then be things like generating or synthesizing audio. And what I mean by that is now not just consuming audio, but either generating audio from some non-audio formats or synthesizing audio, which is to say converting it from one kind of audio to another kind of audio. Tasks under that field would have to do with things like text-to-speech, where, for example, if you've interacted with things like Google Assistant or Siri or Alexa or similar assistants, you would find that you're able to speak to this assistant and get audio input out. And that audio has come from maybe some text-based system resident within the assistant. You might also have voice cloning as a task. So that's figuring out how do you copy the relevant features from some audio and generate new audio that fulfills those features or has those features as the original audio. Finally, you might have music generation, which would have to do with figuring out how to actually generate music of different instruments based on some of the features of those instruments. Now, like I mentioned, we're going to focus quite concretely on ASR, or automatic speech recognition, and something to appreciate, understand about ASR is, and many of these other ML tasks within audio and ML generally is they often are pipelines. And what I mean by pipeline is they're often series of different tasks that are done one after the other, or sometimes in parallel, to perform the entire operation you're trying to do. So you might have in ASR, for example, some level of pre-processing. Now, ASR, like I would remind, is how do you convert speech from some audio, and how do you recognize what speech is resident within some audio. So whether that's to convert it into text or to do something else with the speech, but how do you recognize sort of voice parts of a speech audio? Now, like I mentioned, this starts as a pipeline of tasks. We start out with pre-processing, which takes the audio signal and we try to convert it into a useful or usable format. Also, before actually using this audio, you might also want to extract the relevant features. Because if you think about audio, for example, you think about it in some format, the format it's in, whether it's an MP3 file or a WAV file or some other kind of audio, maybe even audio that is part of a video, like audio in an MP4, for example. You might want to extract what are the relevant features from that audio, and how do you use those features to get what you want out of your entire ML task you're trying to perform. When that's done, you typically want to then do the actual processing. So what is the actual task you're trying to do? And this is often called inference. So inference is typically a term used to describe the process of taking some data and figuring out and learning attributes about that, data in a process of training the model. But now inference would be applying that trained model to perform a particular task you're trying to do. Now, especially with audio-based tasks like this, you typically have two types of models that are used to perform inference. Now, they have historically been two different models, but one of the things I'll go over today is how models like Whisper are now joint versions of these models. So you have the newer versions of these ML models being both acoustic and language models. And what I mean by that is an acoustic model itself would typically be used to find out what are the potential word sequences from some audio. So if you have some audio, for example, maybe with some background noise or with some additional sounds in the audio, where you have someone pronounce A within the audio, the job of the acoustic model is to say phonetically, we have an A sound. How do you find out, given some audio data, how do you find out that the A sound is resident within that audio? That would be the job of the very first model, the acoustic model. Now, you might also have a language model resident within this task. Now, the language model the job of the language model would be to improve this process of generating audio by making sure that the generated sequences are linguistically likely. What that means is you might have an audio, you might have the output of the model, say, given some audio, let's say some background sound with A said in the middle of the audio. The model will typically have a probability distribution of the possible sequences in that audio. So it might say, for example, with A, that it knows it is the sound A to 95% probability, but it also feels it might be the sound A to 5% probability or to a 2% probability. And you have these different sounds distributed in a probability distribution where the model says, this is what I think most likely word sequence or phoneme in the audio is, but these are also quite likely. Now, if you think about that process, you might want to have a language model that will then look at those probable sequences of the acoustic model and figure out, in the context of what I know so far about the rest of the audio, what could be the most likely linguistically. And by linguistically, I mean that if you look at an English sentence, for example, the one I'm saying right now, there is there's a probability distribution of what the next word I might say would be, right? So you might have the model guess that this sound might be A or it might be A. But if you think about the previous sequences that have been generated or the previous words that have been generated, so something like the apple fell from the tree. Now, the acoustic model could guess that at the points where the audio had a sound that sounded like tree, to 50% probability, it thought it was tree. To another 50% probability, it thought it was some other sequence that doesn't make as much context in light of the rest of the sentence. So it is the job of that model to sort of figure out what is knowing about how English works and like what is the distributions of different sequences in English language, what would be the most likely to come next. Finally, you might have some post-processing. So that will typically be correcting mistakes. So if, for example, you've worked on this acoustic model, you've worked on the language model, and you want to make sure, for example, that every text generated ends with a new line or has some particular formatting to it, you would add all of those in the post-processing phase. Now we're going to actually build a really simple audio classifier, and this would be somewhat related to a classification task within audio machine learning. And now to take you through the way this could work, I would we'll need to go over a few sort of basics of sound and of how sound works. Now to go really quickly, because I do feel quite run out of time. Sampling is typically how you go from a continuous signal to a discrete signal. So how do you go from a continuous uncountable signal like sound, where you can get a value at every point, to a discrete signal, because you're working with computers that have a digital representation. They have a fixed memory. You can't put in infinite values into a computer. Now, to just show a quick demo on what sampling looks like and feels like, what I have here is a demo of how audio data really works. Now, if you see on the left, this is, I guess, a representation of a continuous signal. Now, if you think about it a bit more, you notice that this isn't really continuous because it is on a computer, so it is discrete in some ways. It is far more discrete, so like there are much more signals. So it is far more like a continuous signal than the one on the right. Now, the one on the right is a sampled signal. Now, what I mean by sampled is you have on the left 1,024 samples. So for each sort of duration, we have 1,024 samples of the audio. And on the right, you have 256 samples. What that gives you is a less accurate model of the audio data, but one that is easier to store. Now, one of the other things we might want to do with this, with feature, is feature extraction, which is trying to figure out what are the relevant pieces of that audio. And what I would like to show here is a concept of vowel formats. Now, if you think about the slide we had previously, you would have seen that we have, for example, let me just go back there really quickly. When you play some audio, you see that the signal isn't a clean sine wave. It's more like a merge of multiple sine waves within the audio signal. That's because when we speak with multiple frequencies embedded within the sound. So there are multiple ways in which there are multiple different sort of frequencies within the audio signal when we speak. Now, what you see on the next slide is a frequency distribution of the particular audio. What that means is the audio from my voice right now has a frequency around 500, but there are also much higher frequencies within my audio. Now, one way to think about that, or to appreciate how that works, is if you think about a sound that is has a very high frequency. So I had something to show here where I have sort of a book, and if you, for example, like you would find that if you like do a sound that is has a high frequency, you would see much higher a much higher amplitude of a high frequency here. But if you have more low frequency sound, you would see much higher frequencies here. Now, why that's important is that in terms of human speech, consonants like have very high frequencies. So if I pronounce a sound like you see that at the end of the sort of frequency band, you have a lot of amplitude. But vowels, on the other hand, have much lower frequencies, like or e or ah. You'd find that the frequency distribution moves closer towards the lower frequencies. Now, even amongst vowels, there are vowels that have higher frequency distributions and some that have much lower frequency distributions. So E, for example, has the highest sort of what are called like the vowel formants. So a formant here is two different high energy frequencies. So just because of the way the human mouth and vocal system work, the way we pronounce E makes it such that our vocal sort of cords are more open, and when they vibrate, they produce a much higher sort of frequency distribution. When we pronounce a vowel like "or," we then have more sort of lower frequencies in that distribution. Now, I'll go quickly past this because I do feel we're quite running out of time, and I have some more stuff to show. But something this sort of frequency distribution is how we figure out what are the relevant parts of some audio. Now, if you play some sound like beat, what we see is, and you may not be able to hear this because of how it's playing, but when you play sound like beat, what you have with E is a sort of like high frequency distribution of the sound, more than when you pronounce a sound like boot. Now, if you even pronounce boot itself, you do feel like it's somewhere sort of lower in your vocal system in a way that you're sort of vibrating a bit more and producing sort of much lower frequencies. Now, what we essentially do just with machine learning with audio is just to figure out what are the differences in the frequencies of all the sounds. Now, what you can do here is, and I can show what this looks like, is if we look at beats, for example. Now, this is just a screenshot or snapshots of what I showed here earlier, where you're taking the different formats and figuring out like what are the differences between the two formats. Now, I told you like E is the one that has the sort of highest distribution, and then something like U is the one that has a sort of a lower frequency distribution. Now, what you can do with that is you can actually plot the two different points and say, this is what, in terms of the formats 1 and 2, this is what beat looks like, and this is what boot looks like. And you can label those audio samples as the E in beat has this distribution, and then the U in boot has this distribution for the two of them. And what you can do with that is if you find some unknown word, so this is some new unknown word we have not played yet, and you can just plot what is that sort of frequency distribution of the audio. And you can try to figure out what word has been pronounced here. And quite quickly, like if you start this, for example, what you see is if you take this unknown word and just plot the frequencies, you'll find that it is much closer to boot than it is to beat, just because of the frequency distribution of the vowel within that sound. And now if you do some like SS1 math, I guess here, and I try to not put a lot of math into this talk, so this is probably the only one I'll show. But this is the Euclidean distance, or distance between points on an XY graph. Now, if you calculate that distance between 2 points, all you're saying is the distance between unknown and beat is about 791 units, and then distance between the other one and the unknown word and boot is about 78 units. And with this way, we can figure out that the word in this sequence is much more likely to be boot than it is to be beat. And that is essentially how a sort of, I guess, simple version of an audio classifier works, where we know some information about how some sounds work when a word is pronounced. Just because of the way biologically, the way the human system works, we can figure out based on some new audio. And by the way, these features are general to all humans. Like all humans have, to some extent, a very similar sort of distribution. Like very few people, or no one would be pronouncing E at a much lower frequency than they pronounce oo, for example. So this is how we sort of figure out what the likelihood of different words are in some particular audio. I wanted to speak quite briefly about Whisper itself, but I do think my time is already sort of ramping up. But I would say briefly that in terms of features, what Whisper is essentially a much more advanced and much more robust version of a model like this, where you can do a variety of things at the same time. You can do both figuring out words in different languages, but you can also translate speech and identify a particular language in some audio. And a bit about how it works is it uses something which is related to what we've just talked about, but a bit more advanced, called a log-mail spectrogram. And what that is earlier on, we showed a frequency distribution of some signal, but we only showed that for a particular time. So for example, you were seeing that as I was speaking to the microphone, we were getting distributions in real time. But what you might want to do is look at the audio over time and look at all the sort of frequencies over time. And it's also done in the log scale instead. And it is sort of called the log-mail spectrogram. And what we do next is, and again, this talk would be much too short to go over this in detail, but just to give some kind of appreciation of how a system like this is formed out of different parts. What you do on the sort of left is then try to extract what are the important features of that spectrogram. And what Whisper uses is a sort of transformer neural network, which we didn't really talk about in the previous one, but still does the same sort of general task of finding out what are the features here, and like how do I figure out what is most likely to be the feature I need in the audio. I'll speak briefly about with these, and I think the slides will also be available after this for those who might be curious. But essentially, Whisper itself, just the goal of this slide is just to show that at the end of the day, with the input and outputs, Whisper itself is really similar to the simple classifier that we have built, where it is trying to figure out what is likely based on stuff that I already know about how words and the human vocal system work. And this is my sort of final but one slide, talking about, for people who might be interested in stuff like this, what are the open problems. One of them I really wanted to highlight is localization. As is something you see if you read about Whisper, read a blog, read paper about Whisper, is we do still have a need for better data, especially for I guess less popular or less Western languages. If you look briefly at the table I have here, you have Yoruba on the far right, which is one of the only two Nigerian languages that Whisper supports. So Whisper only supports Yoruba and Hausa out of Nigeria's sort of tens and hundreds of different languages and dialects. And the numbers show the sort of accuracy or error rates rather of Whisper. So Whisper has around like 106 points of sort of word error rate. While a language like the far left, like Swedish, if you look at how well it does as you get better models, it goes down to just about 8% errors for the best Whisper models, while Yoruba remains at sort of in 94.8 sort of error rate. Now that goes to show that because of not having, I guess, a lot of data, public data available that are labeled with this word, this audio pronounces this word in Yoruba, or this audio pronounces another word in another language, then the models themselves don't become good enough for those tasks. We have accessibility. The models can get better and easier to use, and we also can try to speed them up and get them run on lower end devices. Now, just in terms of resources, I've also put here a number of places to get started with. And these are projects or these are courses that I found quite interesting in my own personal learning. And hopefully anyone else who's interested in them would also find them useful. So thanks so much. And let me know. I think I did go over time a bit, but if there are any questions or if there are none, then thank you so much for having me.